Thanks, Karen, and thanks for having me. It's an honor to be here. Yeah, so just to introduce myself briefly, my name is Nick Schrock, and I'm the founder of Elemental, the company behind Dagster. In a previous life, I worked for Facebook from 2009 to 2017 and started a team called Product Infrastructure. And that team was responsible for making our application developers more efficient and productive. And we built a lot of internal stuff, but we also ended up creating open source technologies such as React, React Native, and I personally created and was the tech lead for the first couple of years of GraphQL. And that we open sourced all those technologies and they kind of were broadly adopted. And after I left in 2017, I took some time and started to figure out what's next. And I was asking traditional companies and technology companies what their biggest problems were. And the idea that data infrastructure, ML infrastructure, and all related activities were the biggest problem kept on coming up over and over again. So I looked into it, and what I saw was the biggest mismatch between the complexity and criticality of a problem domain and the tools to support that domain that I've ever seen in my entire career. And when I see something like that, I'm just totally compelled to work on it. And after a lot of an examination and deep introspection, well, introspection is the wrong word, deep inspection of the domain, it really struck out. Orchestration really struck out at me as a critical point of leverage in data systems, especially in terms of the opportunity to improve it and even redefine it, as well as it's this critical point of leverage in data systems. So what is data orchestration? This is a fairly technical audience, so I won't go too deep into it, but when a person or a team wants to put a data asset in production, and by asset, I mean a table, a file, and a lake, a trained model, that's not done in a vacuum. Data must come from somewhere and go somewhere, right? Like if you're building a computation in a data system, typically you're consuming upstream data from some other team or person or ingest system that's producing it. And therefore, you need a workflow manager or orchestration system to model those dependencies and ensure that those computations that produce data are scheduled and ordered correctly. But we at Dagster really think is orchestration not as that problem to solve, but an incredible opportunity. And the reason why is that orchestration is this natural center of gravity for the data platform. I like to call it the town square. Like I said before, anyone who puts a data product in production has to show up there. They bring their own toolkit and their tools, which means that in the end, the orchestrator invokes every single computational runtime, touches every tool, touches every storage system. And we divide the world into kind of three roles that the orchestrator involves. One are practitioners. So these are people who are responsible for the production of data assets. This would be your data scientist, your analytics engineer, your data engineer. And they spend a lot of time in the orchestrator, and the graphs they end up building in the orchestrator actually end up being the structure of their data application that they're building. So we think it's really important to treat it as such and treat it like a proper software artifact with a dev and test lifecycle and applying a proper software engineering lifecycle to it. There's other stakeholders too, right? Well, other groups. There's another group called stakeholders, and those are people that care about data assets. And often these are ops people, business analysts, and practitioners from your peer teams, and they care about the data consumed. And we want to be able to kind of self-serve on top of the platform and even do operational tasks. And lastly, you have platform folks who are responsible for the data infrastructure and support practitioners and stakeholders. And really, one of their primary jobs is to enable end-to-end ownership by practitioners over their data asset production. So practitioners shouldn't have to think about infrastructure. And there's a natural center of gravity for all this, and that's the orchestrator. And we really think the orchestrator needs to be designed with the full data lifecycle in mind. That's what I'm going to talk about today. I'm going to talk about Dagster. So there's existing orchestrators and workflow engines. What do we hear from users of those systems? These would include, the dominant one is Airflow, but there's Luigi, Argo, lots of different systems. And what we hear are things like this. During the development test phase, when they're working, they can't develop their DAGs locally. They can't test their DAGs. In effect, when they hit the orchestrator, kind of everything grinds to a halt, because it's very difficult to run locally, and typically you just wait until you deploy to run it, actually, in most organizations. Next, these orchestrators frequently were conceived to solve this one specific problem, but they didn't conceive of themselves as platforms of multi-tenant teams, which means that, for example, in Airflow, DAGs from one team coexist in the same process as DAGs from another team, which coexist in the same process with Airflow itself. And this means it's just like a very unstable environment where one team can bring down another and all their dependencies intermix. And this is the big problem. And then lastly, the monitor observe phase, which is when you actually have to execute and monitor these things. This is also notoriously challenging. What we hear is that this is incredibly difficult to debug. I don't actually know what's going on inside of one of these DAGs that I might not have written. And then as a result, there's kind of this mess of data assets that's created, and no one knows where the data comes from. If you find some arbitrary table somewhere, it's very difficult to trace back what computation or pipeline produced it, and therefore navigate through the organization. So there's huge opportunities here to improve life in every phase of the life cycle. And this is how we kind of conceive of this, the outcomes that we want to achieve in each of these stages. So in develop and test, we want to be able to efficiently and quickly build well-structured, testable data computations. And we believe the orchestrator needs to be designed with this in mind in order to achieve this outcome. Next, we want to be able to reliably deploy and schedule and execute these computations, and do so in a way, reliably means that your team can't bring down another team, and generally there's better isolation in these systems. And lastly, we want to be able to track, monitor, and manage asset production. And we use those words carefully because the end goal of these systems is to produce data assets, produce these externalities that outlive the run of a pipeline. And we believe it's really natural and critical, actually, for an orchestrator to be asset aware, because in the end, that is the outcome that you, the data practitioner, are trying to achieve. Now, the rest of this presentation is framed with a live demo, so wish me luck. And what this live demo is going to do is we're going to simulate a bunch of teams working together to achieve an outcome. And in this case, they're going to download data from Hacker News and build a story recommendation engine. And then also, if we have time, an analytics engineering team is going to build a derived set of tables for analytics dashboards. So this is one of these classic multi-team, multi-technology data applications. And we're going to focus on the first stage written by data engineers, where we download Hacker News data. I guess I'm kowtowing to the, or catering to the conference here. I'm going to focus on the Spark component of this, or the pipeline, the part of the data application that uses Spark, and using Spark to compact that data into Parquet and load it into BigQuery. So let's talk about the dev and test life cycle of data applications that are hosted by orchestrators. Why do we think this is important? Well, we believe that this is the status quo in most data systems, meaning that too many errors are caught way too late in the data application lifecycle, meaning that too many errors are caught in production or in staging environments, which take a long time to run. And we believe that lack of support and design for testability and local development in the orchestration layer is a big part of this. And this represents a huge opportunity, because where we want to go is we want to sort of flatten the curve, to use a very 2020 term. And that means that we want to push as much development, as much error detection, as early as possible in the life cycle, while acknowledging that because of the nature of data, that some errors can only be caught in production, such as data quality tests. But the reason why this is such a massive opportunity is that at every stage that you go later, it's an order of magnitude more expensive. So this curve shifting represents, in aggregate, a huge order of magnitude improvement in developer productivity, therefore system quality, therefore the general happiness and life satisfaction of the developers that work in these systems. So we believe this is incredibly important. So I've been talking for a while. Let's actually talk about some code. So this is what Hello World looks like in Dagster. It's an open source project. You can pip install it. And so you construct pipelines, which consists of these nodes of computation called solid. So solid is effectively a vanilla Python function that's decorated, and you can run whatever code you want within it. And then a pipeline constructs the dependency graph. So here, the hello world function invocation doesn't actually invoke hello world. What it does is it constructs a single node dependency graph. And then as you note, you can actually just in a lightweight way, execute this directly in process right from within the script. If we go to more of a real solid, and this is the one we'll actually be running, this is kind of something that does real work, right? This is the solid, which is downloading the information from Hacker News. And I want to point out a couple things here. One is that solids are functions. They take in inputs and they produce outputs, and they're supposed to be logical inputs and outputs. This is contrasted with, say, like Airflow, which is effectively a graph of taskless, parameterless tasks generally. These inputs and outputs are also optionally typed, and that typing information is surfaced in our tools. As I mentioned before, the body of solids can be arbitrary Python. And then lastly, and this is a really important point, is that you'll notice there's no calls to toCSV or toParquet in this solid. This is purely expressed in logical terms. And this is just a critical property to making the framework sing in terms of embracing separation of I/O and compute. Right? So we believe that these should be effectively pure functions as much as possible, and that the control of where the inputs and outputs come from and are persisted should be controlled on a different, with a different separation of concern, with a different abstraction. So let's actually hop to the demo here. So the moment, like I said, the moment that you structure your code in that fashion, you get to load it in tools and use it in tools. And so this is our web tool. So this is literally on the command line. I should probably actually do this in the demo. I just typed Dagit and it loads this. There's no infrastructure dependencies. And you can go right in here. I'm going to navigate. We have these nice global search. We try to make this a consumer grade UI, actually. You can navigate to your download pipeline. And here's that solid that I had written. And you'll notice that kind of all the information that I adorned the function with is exposed in this tooling. And you can load it without infrastructure, which means you can just git clone a code base, run Dagit, and immediately get up to speed about what's going on. It kind of moves the pipelines into units of documentation rather than to just kind of deploy units of execution. You can also use this tool as sort of a local IDE for DAGs. So we have this thing called the playground. This allows us to launch our computations. Imagine we're doing local development here. I'm going to go here and imagine I made a mistake. I am bad at programming. Wow, I'm typing accurately today. That's not always the case. Now I'm going to launch this execution. And so this is actually just launching a process on my laptop. And you notice we have all these beautiful tools at our disposal. So we have this live updating Gantt chart. It's showing what's going on. You'll see this kind of in a more realistic context later. We have the structured event log down here, which is a basis of a lot of our debugging and monitoring flows. So I see there's an error here. What I can do is I can actually filter down to the failure. Boom, how fast was that? Then I can view this message and say like, oh, okay, interesting. This error happened at line 49. I flip back here, I fix it. And now, for example, I can say, I want to restart this from failure. So imagine the computation before it was incredibly heavyweight, it saved some file. This just allows you to pick up from where you left off, right? Which is incredibly useful when developing these things. Going back to my deck here, this isn't just a local IDE. We also really believe in local testability. And you can invoke these computations very similar to the way you just invoke normal Python functions. You have to, in certain cases, you have to build this context object with the system context object, which is flowed through the compute, which I'll explain later. But we can just unit test the solids right here and execute these tasks in isolation, which can be integrated there. Other focuses, I'm going to give you a couple of examples of where we really focus on early error detection. So here's an example of cycle detection. So this is from a presentation last summer at the Airflow Summit, where they're explaining how to test Airflow DAGs. And this is the code that's necessary in order to detect cycles in an Airflow instance. So effectively, the person here had to re-implement the logic of the scheduler to load all these DAGs into process, because Airflow's model is super tied to a long-running scheduler process. Whereas Dagster's pipelines, our version of DAGs, are pure in-memory constructs, which you cannot construct if they have a cycle. So literally, you just say a certain pipeline. If it was able to be constructed, you're good to go. Here's another example. We have an opt-in schematized config system for parameterizing our computations. And here's an example where we parameterize this thing and we say, hey, there's a partition date and it requires a string. And you notice that on the right, we wrote a test where we fat-fingered and we said partition date X, and that was bad. Well, as a result of having a schematized config system, we can provide incredibly rich errors. And we can clearly see that, hey, there's an unexpected config entry. We're missing this required one. We can fix it immediately rather than having some opaque key not found error or just deploying this to production accidentally with this error. The moment we implemented this, we found that it really increased our productivity, even just internally in our code base. But testing has to go beyond what I would call this structural testing, which is about the structure of the graphs and the structure of the config. You want to be able to test the business logic, but the issue is that's really difficult in data systems because data systems often rely on very heavyweight external dependencies. So, for example, I was able to execute that thing on my laptop because we had what we call a test mode, and it had different resources. So I was using Spark. I launched it on my local laptop, and I was persisting the intermediate results to the file system. But when we're about to deploy it, we need to switch, and we need to run that Spark computation in EMR, and we need to persist the intermediates to S3, but we want to hold our business logic constant. So we have this resources system, and a set of resources indicates it's the business logic's relationship with kind of its external computational environment. So you might have noticed that in the code example here. So if you look at this, there's this context object, and through the context object, you can access resources. And what this structure allows us to do is like everything in computer science, you can solve it with a layer of indirection. It allows us to swap in different versions of that resource without changing any of the business logic. And so, for example, in our test mode, which I ran locally on my laptop, we're actually kind of using a snapshot of the API result from the Hacker News pipeline, or not pipeline, the Hacker News API. But in prod, we're going to go against it directly. And this ends up being a very powerful abstraction layer by which to structure your applications. Okay, I've talked a bunch about the programming model and a ton about the APIs. Now let's actually deploy and execute. I'm going to give this a surface level explanation, given that our limited time. But I want to go over the structure of like what this looks like when you actually deploy it to a production cluster, let's say Kubernetes or something. We have a couple long-running services. One is our run scheduler. So it's a long-running service whose job in life is to schedule runs. And then we have a web server, that tool we call Dagit. That's also our deployed web server. And the critical thing to note here is that the daemon and Dagit interact with user-defined code, the code that you write, over an API layer that crosses a process boundary. And this is what makes this such an operationally reliable system, meaning that if you push up bad code, let's say that for some reason totally blew up, it wouldn't bring down the whole cluster. All it would do is the system would note that, hey, I couldn't bring up this container, it would alert the user, and it wouldn't affect the operation of the system itself or the other teams. Our run scheduler is this fault tolerant. It's kind of structured to be fault tolerant. So if it goes down, it won't miss any scheduled runs. And I think the interesting thing for those who are familiar with Airflow is that we actually manage sensors in the run scheduler. So we consider a sensor event-based schedule as opposed to a long-running task. And we think this is just a much better way to model that concept. And then once the daemon launches a run, we have architected the system to be very friendly to the world of infinitely elastic compute. So we generally allocate a ephemeral computational resource, such as a process or a K8s pod, and then per run, and then its responsibility is to manage task scheduling. So this distributes task scheduling across many more computational resources, which generally leads to system scalability and is very friendly to public cloud architectures. It's a very pluggable system. So I've been talking about Kubernetes because we have the out-of-box production-grade Kubernetes deployment. It's actually pretty straightforward to get up and running. but you can run it on any sort of infrastructure. It's specifically designed to be infrastructure agnostic, as opposed to, pardon me, I'm closing a window here. It's specifically designed to be infrastructure agnostic, as opposed to be saying vertically integrated with Kubernetes. So what does it look like to actually interact with this thing in prod? So I'm going to close this window and go to this demo site. But this is actually running on a K8s cluster in AWS, and you can use very similar tools. So let's navigate to that same download pipeline. But in this case, this thing is deployed. And you'll notice that we're executing in production mode. And I can still launch this with ad hoc computation. It's also running on a schedule, actually. I actually probably should have turned that off before the demo, but that's okay, it won't go on. So here you can see it's actually running on a schedule as well. We have this nice scheduling API. But if we go back here, I've launched it with ad hoc compute. You can see here, navigate to the runs for a particular pipeline. Let's navigate to it. And now it's actually spending some time booting up a Spark context, and we're executing here. But the same exact tools that I showed you in local development also work in a deployed context. Let me make sure that this kicks off correctly. Hopefully the demo gods are being friendly to me, and there we go. And so now this is executing in a Kubernetes context. And you get the same exact tooling, and it's really, really nice. Okay, so last stage, we're going to talk about observing and monitoring. And we're going to talk about this in the context of the data science pipeline. So if you recall, way back at the beginning of this talk, I explained how we're going to have downstream data science teams consuming the data produced by the data engineering team. And it's going to fetch data out of BigQuery and build a recommendation model. So, just stepping back for a second, what's interesting about the data platforms is that it's multi-role and multi-tool. So there's multiple types of people that interact with it. So a mature data platform must think across roles. So for the beginning of this talk, we kind of explained how a data engineering team or a data platform team could build the front end of this pipeline end to end, right? But we really want that team to also abstract away all the infrastructure concerns away from, say, data science and analytics engineering, because we want them to focus on their business logic. But we still want data science to own the dev and test lifecycle, as well as self-serve their ops. So this is kind of the grid a mature data platform needs to think about. So we're going to show the dev and test experience for a data scientist and their monitor observe experience. So this is the pipeline we're going to demonstrate here. This is actually how you build a pipeline in Dagster. So it's this kind of high-level DSL where you can pass data from functions. But again, this is just building this dependency graph. And so that's how that works. And then what does the actual body of computation look like that someone writes? Well, if you're a Python data scientist, this looks probably familiar. These are scikit-learn abstractions. It looks like vanilla Python code, right? The only Dagsterism here, and this is what speaks to the observer monitoring, is this thing called the asset materialization. So this is the programmer informing the system that we have created or are about to create an asset that will outlive the scope of the computation. And as you see here, it gives various properties about it, which are going to be very useful to the system. So what is an asset? An asset is any entity that outlives the scope of the computation. So that's like a data warehouse table, as a Parquet file on a data lake, a pickled model that's been stashed God knows where. But the reason why we think it's so important for an orchestrator to be asset aware is that your stakeholders do not care about your pipelines. I hate to break it to you, they don't care. The only thing they care about are assets. And so assets are an extremely useful window into the operations of the orchestrator, which I'm about to demonstrate. So let's go back here, and I'm going to go to the story recommender. So this is that pipeline that we constructed here. And if you notice here, there's already a run running. How that happened actually is if we go here, there's a sensor. So story recommender and hacker table news update. And you'll see that this is this live running sensor that polls and detects actually when one of these asset keys in our asset catalog gets updated. And here it got fired 2 minutes ago. And it actually worked. The demo gods are being friendly. And so based on an asset update, the story recommender fired. And now the same trick that I showed you before, or I think I showed you before, we can actually search and find all the asset materializations that have been generated by this computation. So it's, okay, interesting. Here's this asset key. It's how we identify a particular asset. In this case, it's a file in S3. Let's view the asset here. And here's all this information about it, which is interesting. So the number of bytes its process hasn't changed over time. The amount of time it's taken to execute has changed. And we have this structured event log, this immutable log of events that gives us a ton of interesting information about this. But the other thing you can do is that imagine you know nothing about a pipeline, but say you found some table somewhere that looks wrong, and say it's called comment stories. Well, you can actually just go in here and search, look for comment stories, and boom, you can open it right here and navigate right to it and see what's been going on. Okay, its last was touched at 6:53. It has these properties. You can go and you can look back and see the pipeline that generated it. And this is a super, super useful way of operating. If we go back here, I mentioned the sensors, and we think we're going to invest heavily in this area because we think sensors combined with asset awareness is the way that you structure loose dependencies between teams. So imagine that you have team one, that's what we just demonstrate, writes some asset key called foo, and then the sensor monitors that asset key and decides to kick off the next run. And even when we were developing this internally, my teammate who developed the data science pipeline was like, I didn't even know anything about the pipeline. It was incredible. We just decided on an asset key and where that lived, and then I was off to the races. I am running a little short on time, so I'm going to skip the last part of the demo, but I want to briefly talk about analytics engineering and DBT. So we get a lot of questions about what is the relationship between Dagster and DBT. We view them as very complementary systems, actually, with highly aligned values. DBT graphs are effectively DAGs of functions that consume and produce data, and they're peer functions because they're just select statements for those of you familiar with DBT. And so we really visualize this as if you're enabling a DBT workflow, integrating with Dagster, you're keeping that dev and test lifecycle that analytics engineers know and love, but you use Dagster to orchestrate DBT computations with computations which are not in SQL. For example, Spark computations. Although Spark actually can technically use Spark SQL, but it typically doesn't. Or DBT can use Spark SQL, but typically doesn't. It's easy to do this. You can just integrate it. We have an out-of-the-box DBT integration, where you just point it at the project and profile directory. And I'm going to skip the last demo. So, conclusion, orchestration is a huge part of data platforms. It's a huge problem. It's a huge point of opportunity. We think you can improve developer productivity, and it's this massive leverage point for both a data platform and ecosystem-wide progress. Dagster really thinks about the entire end-to-end process, all the way from developing and testing your data applications to deploying and executing them in a reliable way, stable way, and also monitoring and observing the results. And then really, Dagster allows platform teams to tailor dev workflows for each role and enable self-service. So thanks for listening. We're an open source project, so we're on GitHub. You can go and navigate, star us, come to our Slack, very active and friendly Slack. And we've been working really, really hard on our docs site. And this is totally open source. So you could, right after this presentation, go pip install and go nuts. And with that, Q&A. And we're apparently might be kicked out of this in a couple of minutes, but I'll let Karen take over.
Thanks, Nick. Yeah, the speakers have a chat with our operator too, so he's giving us the warning that we have 2 minutes left. So we do have a couple questions. Maybe we can get to one, maybe two, really quickly.
Yeah.
So Nick, first question, maybe last. Do you see Dagster being used in a CI/CD cycle? If so, what would be a typical use case?
So there's two ways I can interpret that question. One is, can Dagster be used to power a CI/CD system? We actually have users who have explored that. It's like orchestrating a Dagit compute. If you're talking about within the context of an existing CI/CD lifecycle, absolutely. So this is one of the goals of the system. meaning that, as you saw before, you could execute our pipelines in different modes with a lightweight Python API, which means that we anticipate it being run in local testing, in a CI/CD pipeline at many different stages. So yes, nearly all of our users integrate Dagster within a proper CI/CD pipeline. And it's one of the big value propositions of the system.
All right. Well, I think with that, we're going to end it here. So thank you so much, Nick. Thank you, Marianne and Allison and Michael and David. And thanks everyone for joining us. Really happy to have you. And I hope you enjoy the rest of the conference. All right, everyone, take care. Thanks.